I have already clicked the live button. Yeah, we are live now. Okay. Very good morning to all the participants. This is Dr. Devashish Sharma, Assistant Professor in the Department of Mathematics, Gurucharan College, and the coordinator of this international webinar series on applications of mathematics. So we have basically organized this international webinar in order to highlight the importance of mathematics in our day-to-day life, the various areas where mathematics is being applied, and to motivate students as well as teachers, research scholars to appreciate the applications of mathematics. So in order to organize this webinar, we have contacted with various resource persons from diverse backgrounds. So today's lecture will be given by Dr. Swapan Mallick, who is a weather researcher at the University of Oklahoma, USA. So we are very lucky to have him with us here. And good morning, sir.
Yeah, good morning.
Yeah, it's actually a night there in America.
Yeah.
So welcome to our international webinar series. We are all eager to hear from you. Let me bring to the stream our head of the department and chairperson for this international webinar, Dr. Biplab Chaudhary.
Good morning.
Yeah, good morning, sir. So I would like to request Dr. Biplab Chaudhary to kindly say a few words.
Good morning. It is my immense pleasure to welcome you all the participants and the resource persons in this international webinar program on applications of mathematics organized by our college, Silchar, Assam. We have received very good response from participants all over India and abroad. In this international webinar, our aim is to expose the participant to a wide variety of applications of various branches of mathematics and motivate the participants to inculcate their mathematical abilities to apply mathematics in a better way. We have invited well-versed resource persons for this webinar series from different fields of mathematics. It will be revealed during this webinar. I hope their deliberation will create enthusiastic attitude towards the application of mathematics. I once again welcome you all and hope your presence will make this webinar series a great success. Thank you all.
Thank you, sir. Now I would like to request our student Ankita to kindly read out a brief biodata of our speaker. Ankita, yeah, you may start.
Good morning, everyone. I, Ankita, got the opportunity to introduce the speaker of the session, Dr. Swapan Mallick sir, to all the viewers. Dr. Swapan Mallick is currently working as a weather researcher in the National Weather Center at the University of Yokohama, USA. He graduated from Kachar College, Silchar, with major in mathematics and thereby completed his post-graduation from Guwahati University in 2002. He cleared the NET exam JRF from CSIR UGC and was awarded the Doctor of Philosophy Award from CSIR CMMSCS Mangalore University in the year 2013. His area of research interest includes mathematical modeling, numerical weather prediction with global and regional models, data assimilation including satellite and conventional observation, observation processing system, forecast sensitivity to observation study, artificial intelligence, deep learning, machine learning, tropical cyclone forecast. Previously, he has served as successively and as research fellow at CSIR Center of Mathematical Modeling and Computer Stimulation, Bangalore. He was a Science Journal reviewer at Atmospheric Research Elsevier, Monthly Weather Review, American Meteorological Society, and many more. Dr. Mallick's numerous research articles got published, and he attended various conference proceedings, presentations, reports, training, summer schools, workshops around the globe. Some of them include the 100th American Meteorological Society Annual Meeting Boston, NCWCP Maryland, AMS 25th Conference on Numerical Weather Prediction Colorado, NCMRWF Met Office UK, etc. Looking forward to an interesting lecture by Dr. Swapan Mallick sir. Over to Debashish sir for continuation. Thank you.
Thank you, Ankita. Without further delay, we will begin the session. Just an announcement. I request the participants to participate in the interactive session as well. So they can put forward their questions in the comments section, live chat section in YouTube, and we will take those questions to the speaker at the end of the talk. Okay, not in between the talk. We will take it at the end of the talk. And we will also provide the link to the feedback at the end of the talk. So at the end of the talk, please have a look at the live chat box. You will get the link of the feedback form. Everyone has to submit the feedback form. Now it's over to Dr. Swapan Mallick to begin his presentation. So I think he will be sharing his screen now.
Yeah, okay. Thank you very much, Dr. Devashish, for the nice organization. And before I start the talk, I'd like to thank all the participants and the Dr. Biplab Chaudhary, head of the Department of Mathematics, Gurucharan College, Silchar, and the principal of Gurucharan College, and all the coordinator, and especially the Ankita, who nicely presented my biodata. So a lot of things she told. So thank you very much for that. So now I'll start my talk. So is it okay?
You can open the. It's okay. The screen is visible. Screen is visible. You can open your presentation file. Yeah.
So
it's visible.
Okay.
Yeah, you can hide that message, pop-up message there. Yeah, it's visible. So you can begin. You have 1 hour for the talk, and then we'll have the question answer session.
Okay. So 1 hour. Thank you very much.
So participants can see your presentation as well as your video. And I think you are being able to see only the screen, only the presentation.
Yes, that's true.
Okay, so I'm going off screen now.
So thank you very much, Dr. Devashish Sharma, and the principal of Gurucharan College, and head of the department, Dr. Biplab Chaudhary, for giving me the opportunity to speak on something or application of mathematics, and it is my great pleasure. So today I am going to present the weather prediction, a real life application, interaction of applied mathematics, statistics, and physics. Since my background is mathematics, especially applied mathematics, and I have done PhD, and my all the work is on the weather prediction related. So it is my huge interest to show the future of mathematics in the different field. So how to predict future weather? This is an application of mathematics. So importance of weather prediction is huge. Starting from the aviation sector, agriculture, and tropical cyclone forecast, there is a huge demand of weather prediction. It is the demand is not only in India but also worldwide. In USA, there is a lot of tornado severe weather happening every day. Cyclone, here it is called hurricane. Every year lot of hurricane is happening. So basically, how much we can forecast accurately, this is the important thing. And we are um, how we are giving the daily operational weather forecast. So, and now I will discuss the application of applied mathematics on that weather forecast research. And so my introduction will be, I will discuss with the especially numerical weather prediction. There are different type of weather prediction, like but today in my talk I will discuss only numerical weather prediction. So different type of weather observation, what weather observation we are using, a concept of data assimilation, and use in our real life. So as we know that applied mathematics is a combination of mathematical science and specialized discipline of science, including physics, chemistry, computer science, and art science, and many more. So this is one word cloud for applied mathematics. We can see that in this word cloud, the application of mathematics is huge, including modeling, computational calculus, industry, sustainability, fluid mechanics, programming, MBA industry, hardware. So there is a huge application of applied mathematics. So our field is a small part, but application of mathematics is huge. There is a nice quotation related to applied mathematics written by Henry O. Pollock, who is a great mathematician from Australia, USA mathematician. He told applied mathematics is mathematics for which I happen to know an application. This, I think, includes almost everything in mathematics. So coming to my topic, how I can use applied mathematics or mathematics in the field of numerical weather prediction. This is the schematic representation. What I am talking today is the numerical weather prediction. The numerical weather prediction is nothing but a subset of atmospheric science, and meteorology is another subset of atmospheric science, and numerical weather prediction is a subset of both atmospheric science and meteorology. Meteorology, study of meteorology in sorry study of meteorology includes atmospheric physics, chemistry, dynamics, with major focus of numerical weather prediction. So in this figure it is clear that the numerical weather prediction is the small part of atmospheric science. Atmospheric science is a huge topic. So this is interdisciplinary subject. So now, what is numerical weather prediction? Numerical weather prediction used mathematical models to predict weather in weather condition includes heat wave, severe storm, tropical cyclone, heavy rainfall, flash flood, and many more. In agriculture sector, in other words, a quantitatively or numerically or data representation of weather based on a set of model to predict temperature, pressure, wind, rain, it is over the prescribed domain. So to do numerical weather prediction, we need some knowledge of applied mathematics, statistics, physics, computer science, and chemistry. Although chemistry, in my specialization, chemistry, I am not working on chemistry subject, but there is an application, and especially I'll focus on applied mathematics and statistics topic, and these are the most important topics or application in numerical weather prediction, and obviously including physics. And computer science is also important, because computational nowadays numerical weather prediction need computer, high performance computer. So we can't run this operational model in our laptop, small laptop, or our personal computer. It needs the huge computational power, high performance computing system. I'll discuss in my later slide. So coming to, I'll start from some basic concept of numerical weather prediction. What is it? Numerical weather prediction. It is nothing but a model. It is the it is a model which needs some input data, and it will give some output data. So there are basically three steps. Step one is the input data. Step two is the prediction or model prediction, and step three is the output, which uh, which we'll uh, discuss after one by another. So in step two, to do forecast, we need some model. Generally, different models are there. Global circulation model, we are using global model, means whole our earth planet, or sometimes mesoscale model. Mesoscale model nothing but the small domain. So I'll also discuss about this. So these are model, or these are based on equation, this model. So this model requires input. For input data preparation, step one, we do observation processing system, observation processing system and data assimilation. For step two, for prediction, we are using model run, and for step three, the output data, we have to do post processing or forecast verification. So this is the schematic representation in my talk today. So I'll discuss each step one by another. So I'll start from step two first. So first, what is the model, or what is the prediction system? So numerical weather prediction model are nothing but a set of partial differential equation and other equation that describe the dynamics and thermodynamics in the earth atmosphere. So partial differential, I'm considering that everyone knows the differential equation, and partial differential equation are the equation with multiple variables. So there we are using the partial differential equation and other simple equation, and maximum all of the equations are non-linear. So in that model, we need the equations, initial and boundary condition. The almost every equations need initial and boundary condition, and to solve this nonlinear partial differential equation, we use numerical approximation. So we solve this equation by numerical method. And for physics option, we use the parameterization, because the atmospheric process has a physical process. So how cloud forms, how rain forms, how this molecule, this pressure changes from one location to another location. These things, this parameterization scheme is used. And for domain, we need the domain. Domain means the region where we are interested to produce the forecast. Is it limited area model? This is small. Suppose we are forecasting over only Assam or only Silchar. This is a small domain. But if we forecast all over India, then we need bigger domain. And if we forecast whole globe, then it will be a global model. So domain is another important choice of domain, because the location wise, in our weather prediction system, we need the information about the domain, which domain we are going to predict, because different area all over world has different characteristic, weather characteristic or physical process. So coming to the equation of numerical weather prediction, th- basically we are in numerical weather prediction, we are using a set of nonlinear differential equation or partial differential equation that are used to approximate the atmospheric flow. Atmosphere is nothing but the fluid dynamics. I remember my master's level when I was doing a master's in Guwahati University. That time I learned that fluid dynamics. My specialization was in fluid dynamics. That time I didn't know how to use the this equation in real life exactly. But after that, when I was started doing the PhD, that time I realized that okay, this what I learned in my master degree, these are the real life application in the numerical weather prediction. We can directly use this one, and many interesting things I learned that time. So this differential equations we are using in the numerical weather prediction. These equations are the continuity equation, which based on the conservations of mass. Conservations of mass is nothing but the theory of conservation of mass stated that fluid mass can neither be created nor destroyed. We can only change from one state to another state. So first one is continuity equation based on conservation mass. Second one is equation of motion, which is based on conservation of momentum, which is nothing but the Newton's law of motion. The conservation of momentum also state that momentum can neither be created nor destroyed. So based on the equation of motion, the ba- basic Navier-Stokes equation looks like this way. So Navier-Stokes equation is the equation of motion in fluid dynamics. This equation represents this is the general form of equation where this q is the velocity vector, rho is the density, and this is the material derivative of the velocity vector. This equation represents the equation of motion in general form. Now it may convert in our atmospheric science or for numerical weather prediction. We have to convert. We can't use this equation directly to solve the equation of motion in atmosphere. So we have to convert it in spherical coordinate, and the solution obviously in numerical approximation. Now third equation we are using a thermal energy equation, which is based on conservation of energy. Conservation of energy also stated that energy can neither be created nor destroyed. Only energy we can transfer from one form to another form. So these are the basic equation or primitive equations which generally we are using. Now, so the in atmospheric numerical weather prediction, conservation of mass, one equation we are using for air and one equation for water. Conservation of momentum, three equations are there. Conservations of energy, one equation for first law of thermodynamics. Relation between density, pressure, and temperature, the equation of states. These are few main equations we are using in numerical weather prediction. So but these equations may vary from model to model or different region to region or domain to domain. but and for obviously for different uses. But the concept is same. Form may be different, slightly different, but concept, the equation main concept is similar. So these are the, I'm showing these are the general equation form of equation of motion. ECMWF, European Center for Meteorologic Medium Range Weather Forecast. This is the European Center. They are this we are generally considered one of world best organization for weather prediction. So these are the equation they are using in their ECMWF model. So east to west wind, these are the equation of motion for U wind. This is the equation of motion, and for north to south wind or meridional wind V, uh, this is second equation. And for temperature prediction, temperature forecast, this is the equation. Generally it looks like little bit complicated, but see, these are in spherical coordinate system, which are the Navier-Stokes equation. So if we convert in general what I have shown in my last slide, the general form of Navier-Stokes equation, if we convert in spherical coordinate means latitude, longitude, and vertical. Lambda, theta. Here theta, we can see that the derivative some places lambda is there. Theta is there, nu is there. So this and these are the spherical coordinate system. Lambda and theta as the longitude and latitude, and nu is the vertical coordinate, hybrid coordinate. So and these are some physical process system. So this looks like little bit complicated, but it is very easy to derive in that form from Navier-Stokes equation. These PU and KU are represent the contribution of parameterization physical process. These are coming from physical process of atmosphere. And this for temperature equation, T is represent the temperature, U and V are the zonal wind, and V is the meridional wind. So the details are available in that ECMWF website, all the equation how they are using. And these are the moisture equation, moisture or humidity equation. So and this is the continuity of mass equation, which for pressure. So we can see that on the main purpose to show these equations are, we can see that this is nothing but the mathematics, fluid mathematics. So basically atmosphere is, since atmosphere is we consider as a fluid, so this equation we are using in uh, spherical coordinate system. Now weather forecasting model. In our operational weather forecasting model, the model looks like this way. This is our globe, our earth, and we consider it like that. These are the grid boxes. So grid boxes in horizontally, we have to divide the grid boxes at different size. How each grid box has different kilometer. So this we call rather horizontal resolution. So first, suppose if we consider the global model, so global model means whole globe, whole earth. So we divide the whole earth in different size of grid boxes. We called it grid boxes. So sometimes grid, what is the distance between each grid boxes? This is called the resolution. So different model. Nowadays, the operational weather agency runs the resolution at few 12 kilometer, 25 kilometer, 15 kilometers. So these are the nothing but the model grid spacing, and this represent the vertical level. So our atmosphere uh, goes up to uh, more than 15 kilometer. So it depends on how many in model, how many kilometers we want to know the weather. So the, so we can divide the level, vertical level, in different level wise, which sometimes we are using pressure level or hybrid sigma level. So that is different. I am not going on that details. So basically what we are doing, we are using these grid boxes or horizontal resolution, and we calculate the variable, surface variable like temperature, humidity, pressure, moisture flux, heat flux, this for each grid boxes. And also in each grid point we have to do the physical process for model, physical process, how how the heat is there, how the cloud is there at different levels. So basically it looks like that. So how from the physical process exchange from one grid point to another grid point. So coming to, so this is the huge to predict sorry to predict the whole globe. We need the huge computational power. Whole earth is a big, so if we divide this earth in a small kilometer, so if our resolution is higher, like 10 kilometer, then we need a large grid point will come, and we need the huge computational power. So it is not at all possible to compute or do forecast for few hours or one day with small computer like small PC or our laptop. So we need the super computing power, high performance computing power. Even if we consider the small boxes, suppose here it looks like the small box over USA. So these are local limited area model. We consider it, we called it limited area model or local model. So these are sometimes 700 kilometer by 700 kilometers. So even in this model, this area also we need the high computational power. So since it is so generally what we are doing for research purpose, like school, college or university, students or students are generally using a small toy models, because the computational power is very less, and it is very expensive also. So it is not at all good to do small any kind of major research with this global model or small model. So today I am discussing about this one toy model, which is called the Lorenz 63 model with three variables. This is the first model which discovered Lorenz to study the convection and instability of planetary atmospheric data data assimilation methods. There is another model like Lorenz 96, also many researcher or many students are using for to do some experiment. This is a good model. Actually, this represent the chaotic behavior of the of a system. This equation, three equations are nonlinear equations with three variables x, y, and z, and sigma R and B are the parameters. Sigma is called Prandtl number, and R is the real number, and B is the parameter. So this is full chaotic system, chaotic nonlinear system. So if we solve this equation for each variable x, y, and z at different time, t is the time here, with the parameters, 3 parameters. Here I will show you the solution of this equation, how this equation, how the parameters change, value of x, y, z are changing at each time step. This sigma value, sigma I consider 10, r 28, and b is 8/3. So how it is changing? So this is the solution of this Lorenz model with 3 variables. We can see I've computed t from 1 to 10,000. So we can see that this is the butterfly effect, where the initial condition starts from x 1.1, y 1.1, and z 1.1. But after some steps, it behaves like a chaotic. So it never overlaps. The point at each time step never overlaps each time. So this is the good representation. This is called butterfly effect. So this is the good representation of chaotic behavior of the model, how model behaves. So this is the another example. If I consider two initial condition, means two starting points of x, y, z. One initial condition is 1.111 and another is 1.1, 1.1, 1.1. So 3 x, y, z I consider two. Green is this and blue is 1.1. So we can see that the starting point, this point, starting points, both are almost similar. It looks similar, but after some times both are goes different way, they are not matching. So we can see that the starting point, although the starting point is almost similar, slightly varies, but after some times the forecast goes different way, the forecast difference is very high. So for that so for that we need the initial dynamical consistent initial condition. Now one of the most challenge in numerical weather prediction is the choice of initial condition. This point, what will be the exact uh, point, what will be the initial condition of the weather prediction, numerical weather prediction? Because we don't know the forecast, what will be the forecast if this chaotic behavior is there, and we know the atmosphere is fully chaotic, non-linear equation, we are using non-linear equation. This is the another good example of only single variable x. Here I plotted the only variable x. We can see that with two initial condition, x not equal to 1, I consider x not this blue is x not 1.1. So their starting point is somewhere here, and it's almost, it looks like the very similar pattern up to some near about 1500 time step, but after that it goes in different way. Two values are very different from each other. So this is one of the nice example of chaotic behavior for chaotic model, Lorenz model. So we need a dynamical consistent initial condition, because we are using the full chaotic, atmosphere is full chaotic. and we are solving the nonlinear partial differential equation. So for that, we need the initial condition, and it should be a more accurate and consistent, because we have just seen that slightly increase in the initial value, the forecast will be different. The noise to signal ratio is very high. The noise is very high. So we need the data so how we can solve this problem, or how we will create the initial condition? The answer is the data assimilation or analysis. So coming to my first slide, what numerical weather prediction. I have just finished my talk, this step 2. What is model? What is global circulation model? So for that, we need the initial data. So this now I will discuss with how to prepare the initial data. For preparation of initial data, as I told, we need the dynamical consistent initial condition. For that, the we are doing the data assimilation and observation processing system. So data assimilation, now I will discuss with data assimilation what is the data assimilation and how we are using mathematics, especially applied mathematics, in the data assimilation system, or doing the observation processing system. Now, the application of mathematics in data assimilation. This is one of the huge area and one of the most challenging area in the numerical weather prediction, the data assimilation. All over the world, only few people are working on that data assimilation, and on that topic we need the huge mathematical concept, and this is fully based on mathematics, applied mathematics. So coming to some basic concept of mathematics, I know it is very everyone knows this kind of equation, but I am just showing what we are using in doing the weather prediction, numerical weather prediction, or data assimilation. So we are using calculus, different type of calculus. So this showing the area, the integration a to b fx dx is showing the area bounded by the two line x from x a to xb. So these are the boundary condition, integration, meaning of geometric meaning of the integration. Then we are using the vector and tensor calculus. So those are doing graduation. During my graduation, I got the tensor calculus in master's level, I think, what I remember. Yeah, in Guwahati University. So just I would like to tell that tensor calculus is nothing but the advanced version of vector calculus. Vector is the 2-dimension and tensor is the n dimension, multiple dimension. So we are using both this vector and tensor calculus. So these are some example of inner product, scalar product, or outer product, how two vectors are multiplied. So this type of matrix, we are using this type of matrix for calculating in data assimilation system. These are the very important, this covariance matrix. This is called covariance matrix, the outer product between two vectors. So these are the variance, this diagonal variance we are using for different types of observation. These are one of more important mathematics in data assimilation. Then we are using linear algebra. Linear algebra is, suppose this is one example of linear algebra. This linear transformation. Suppose u and v are two vector space, and t is the function from u to v, be a mapping, and then the transformation associated with vector vector x, which is belongs to u, to the vector y, which is belongs to u, y equal to tx. So if t is linear, then tx1 plus x2, which is equal to tx plus tx1 plus tx2. Sorry. And for scalar, if there is a scalar r a which is belongs to which is a real number, then t ax is nothing but a tx. And the for adjoint, the for adjoint of t, we are this is the definition of the adjoint of t star. So these are the mapping. We are using this adjoint equation. Adjoint equation is uh, in data assimilation one of the basic concept of adjoint equation we are using in the data assimilation. I'll show you some example how we are using this vector, this algebra. There is some eigenvalue, eigenvector, then lot of things are in algebra which we are using in that data assimilation system. Now, coming to statistics and probability theory, we are using the main concept for optimization. We are using Bayesian theorem. Statistics probability is one of important topic which we are regularly using. So these are some basic definition. If A and B are two events, the probability of B, given that A has occurred, means if we have the knowledge of A, we can calculate the probability of B. Since A is known to have occurred, it becomes the new sample space, replace the original this U space. So these are some definition. What is the probability of A? Just probability number of A set A by number of total value U. And this is the definition of Bayesian theorem. These are, we are using Bayesian theorem to optimize the error distribution or maximum likelihood theorem. So these are normal or Gaussian error covariance. Here I am showing just a few definitions of what we are using in the data assimilation. So for one variance case, this is the definition of normal distribution, and for multiple variable case, this is the definition. This B matrix is the product of this this error, or we called it bias or unbiased case. So these are for multiple variable case. So normal or Gaussian distribution is very important, because what we in maximum cases we are considering our error, model error or observations error, generally in Gaussian form, because it is easy to calculate the mean and standard deviation. So we are using this statistics in our method or data assimilation. So just now I have shown some basic slides of mathematics which we are using. The purpose of showing these slides are nothing but to show how we are actually using the mathematics in data assimilation, or to create the initial condition. Now, what is data assimilation? As I told, we need the dynamical consistent initial condition. So data assimilation is to obtain a dynamical consistent initial condition for launching a weather forecast. So to start a forecast, or to run a model, weather model or any model, we need the initial state, or which will be more accurate. So to create the more accurate, we are doing the data assimilation. Now, this figure is showing that data irregularity. We have lot of observations nowadays. Huge number of observations are available, starting from satellite, surface observations, and radar observations, aircraft observations, then automatic weather stations observation. Huge number of observations are available, but these observations are not regular, means we these are not this uniformly distributed. So for these are irregular. Suppose in over ocean, like Indian Ocean, only few numbers of observations, surface observations are there because there is no land. So only satellite observations are available, and few ships observations are available. Whereas over surface or land, over land, suppose in India, over land, huge lot of observations are available, starting from radar data, land surface observations, then balloon observations. There is number of observations are available. So these observations are not regular, and even we don't know the observations are more accurate or not. So how to utilize those observations? We are doing the data assimilation from irregular data to regular grid point, because model, we need the model in regular grid points. So like that, we need the regular grid point. So for that data assimilation, we need observations, background information from previous model forecast, means from other previous forecast we need background information of the present time, and some background error statistics. So this is the schematic representation now of the observation. I'll show you some observations, what observations we are using in real-time experiment. We are running real-time model, global model or regional model. For that model, we need different types of observation, weather observations. So this is the global observing system. So we can see that the for space, the polar orbiting satellite, different type of satellites are there nowadays. India has the Indian Space Research Organization has its own satellite, like INSAT 3D, INSAT 3DR, then the Saphir. These are related to weather satellite, and USA NOAA, national space NASA, National Space Research Organization, they have their own satellite. So like GOES 16 geostationary satellite, different type of satellites are there. Then aircraft data is there, over ocean or sea, whether ship is there. India has few ships, good ships, and buoy are there. Over land, these weather stations are there. Then these radars are there. So these are the some list of this data. So there is a huge number of data are using in regular basis. So we are using this data in the data assimilation system. So this is one representation of polar orbiting satellite observation. So polar orbiting means this satellite is removing every time all over world. So this is NOAA's 17 satellite. Oh, sorry, this is not NOAA's. This is polar orbiting satellite, and this is the swath. This is the path of uh, this air's data. Atmosphere infrared sounder data. This is the NASA satellite data. So this is the how much data cover at each time step. And this is the geostationary satellite. Geostationary satellite is fixed. it's moves with earth only. So this is the representation of ghost 16 and ghost 17. So sorry, this is not NOAA 17. I put it only NOAA 19. This is polar orbiting satellite, and this is uh, no this is ghost 16 geostationary satellite, and ghost 17. Ghost 16 is the goes east satellite, east, and this is goes west satellite. And this figure represent all over world. This is I took from National Center from Medium Range Weather Forecast India. They are using the global model. So in global model, these types of observation different geostationary satellite is using. This is the inset 3D over India. We can see this is the India. So inset 3D, this is the atmospheric motion vector. And so we can see that the inset 3D, this is Himawari. Himawari is Japanese satellite. This is Himawari. So so this a lot of data are available nowadays to do weather forecast, and these are using in regular basis. Now this is I took from GOES 16 geostationary satellite over USA. So we can see that this image is today's image. Today morning, we can see that sun is rising, and sunlight is coming. This is the visible satellite, visible channel, GOES 16 visible channel. And if we notice that here one cyclone is there, this is one cyclone. This is recent cyclone. It's today's cyclone. Here in USA, sorry, in USA, or not Atlantic or Pacific Ocean, is called hurricane. In the Indian Ocean, it is called cyclone. So in India, we are popular to tropical cyclone, but here in USA, hurricane, we are called it hurricane. So Hurricane Genevieve, we can see that Hurricane Genevieve. So this is the satellite data, every real time data. So basically we are using this type of data also. Now coming to the data assimilation, as I told, what is the data assimilation? Data assimilation is the combination of information coming from model and observation to produce best of the initial condition or best state of the atmosphere. Means what is more accurate, because as I told, our model is behave like a chaotic. So slightly, if in initial conditions slight error is there, the model never predict the accurate forecast after few hours or after days. So in data assimilation, we are using different methods of data assimilation are there. The most basic is the optimal interpolation. These are basically based on mathematics. Optimal interpolation is the simple interpolation, 2 points interpolation. This is the fast use of data, yeah, to doing the regular grid point. Then three-dimensional variational data assimilation is there. Four-dimensional variational data assimilation is there. So three-dimension and four-dimensional variation data assimilation, only difference is four-dimension means x-axis, y-axis, z-axis, and time. Three coordinate with time. And three-dimension means only three coordinate, x, y, and z. Then Kalman filtering with approximation, ensemble Kalman filtering, and hybrid methods. Nowadays, we are very much advanced in data assimilation. So most of the operational agencies are doing either four-dimensional variational assimilation or ensemble Kalman filtering or hybrid methods. But I don't think any operational agency are doing the normal optimal interpolation. Now it's not possible. This is one huge topic of mathematics. This is a huge topic. Means this topic is like here we are using mathematics starting from linear algebra, as I told, geometry, then calculus, tensor, then probability, then statistics, normal distributions. So many things are there. Optimization theorem, how to getting the optimum value. So these we are using. So I'll just show today basics, some basic examples of 4D bar. So variational data assimilation. Variation. I remember this variation calculus is there. I learned little bit in Guwahati University that time. So variational calculus, that concept is coming from there. Variational data assimilation. So in variational data estimation is a method of estimating the set of unknown parameters of forecast model by optimizing the misfit between the solution of model and a set of observation. Basically, we are minimizing the error between observations and model background information or model forecast. So this is called J cost function. J is the cost function. So we are optimizing this type of equation. There are different method of optimization. So here we can see that these are the metrics. Uh, these are coming from background information. So in this equation, J represent this plus this J X. So we have to find the minimum value of, for what value of X not, the value of J is minimum. So this is the optimization method. So we have to find the optimum value of this one. And these are metrics. This B and R the background and observation covariance matrix. And this H is the operator. Here we are using what I have shown in my last slide, that adjoint equation. Here we need the adjoint equation to find the solution of this equation. This is also a non-linear equation, and we have to convert it to linear form. So there is a huge mathematics is there. This is nothing but fully based on mathematics. So I'm just showing the some just the concept of this, how it is doing. So we have to minimize the J, for what value J will be the minimized. So it will give the answer uh, of the value. So that will be used in and that data assimilation. That will be the minimum error. So this is the schematic representation of 4D data simulation system, what I use in National Center for Medium Range Weather Forecast. So just I am showing the basic concept, what we are using. This is coming from model simulation or model forecast, and this is the observation. We are combining this is to getting the analysis increment, which is using forecast. This is UM model. UM model means forecast model, unified model. This is based on UK Met Office model, United Kingdom Met Office model. So we are using the analysis increment UN model, and it will give the short-term forecast. So and for observation processing system, we need the observations. So observations are in different formats are there. So this is the schematic representation of what 4D data simulation is doing. And this I show one example for analysis in increment for temperature 20 meter above surface level. So these are not actual temperature value. This is the difference between the analysis increment, observation minus background, this thing after data assimilation. So we can see that this is minus of the from -5 to +5 Kelvin temperature, and this data assimilation is doing all over globe. So this is the data assimilation part. Now So we are ready. We have just done step 2 and step 1. We have created the input data for using the data observation processing system and data assimilation. So we are ready to run the model. So I have already discussed this second part too. So with this more accurate or dynamical consistent initial condition, we are running the model, and it will give the step 3 output data. So the final output, this is another part of research, or we are doing, many people are expert on this part step 3. What we are doing, post processing on forecast verification. So the question is, how much accurate our forecast, or we can't directly blindly doing the simple after running the model, we can't say that this is the forecast. We have to do verification. So this part, there is many steps we are doing, statistical significance of that forecast. These all are coming in step 3. Suppose another example, few variables we can't calculate, model will not give the that variable, like radar reflectivity is there. Reflectivity one variable which model can never predict directly. We have to do these are these are the past part of post processing system. So in that step 3 we are doing post processing and forecast verification. So now I'll discuss the post processing and forecast verification. Excuse me. Now, this is the part 3, step 3, post processing validation and evaluation. In that part, so we are using many statistical method. We are doing the different statistical method like t-test, then absolute error, how much biases are there, this forecast is how much accurate is the forecast. So for these are some example of uh, statistical definition. What is average absolute error, average bias? So we are doing the this forecast minus observation, which is nothing but the summation of total number of observation and forecast for forecast minus observation, and bias is this absolute value. Then the skill score, what is the skill of that forecast? The skill score, definition of skill score is the mean square error by mean square error observation, forecast by mean square error of observation. So skill score is defined 1 minus mean square error forecast by mean square error observation. So forecast is skillful or not. If the skill score is 1, that means the forecast is perfect, means exact. If forecast is less than 1, then there is a bias, or if it is goes near to 0, then forecast is very bad. So like that we are doing some verifications. So and skill score never once, because our forecast will be never accurate, so it will never count to 1, because as I told that our atmosphere is not linear, it is chaotic, non-linear behavior, chaotic behavior. There is another thing, usefulness. We are calculating number of misses, number of overwarming, number of underwarming. So these are definition. If the prediction is greater than or equal to some threshold value, these are using for cyclone forecast, intensity or track forecast. How many misses are there? How many overwarming are there? So these are some definitions. Then null hypothesis. is our analysis is meaningful or not. We are using the climatology like that, linear regression method, linear debiasing method. So these are some definitions. We are comparing our forecast with these types of equations. So these are some statistics. It is not possible to show all the statistics because there is lot of, in real time operationally we are doing lot of statistics, lot of verifications is required. It depends on the forecast type, what types of forecast is there, because different for cyclone forecast or hurricane forecast, different verifications is there. Then for severe weather forecast we are using different verifications. So I just showed some basic things how we are using mathematics. So now coming to real life application, how we are using the numerical weather prediction for real life application. So before that, I would like to show some potential impact of tropical cyclone. What tropical cyclone is doing? Tropical cyclone is a creating low atmospheric pressure, wind, huge wind, and rainfall. For rainfall, flooding is there, and then flooding in coastal areas. So it will damage the vegetable crops, and obviously loss of lives are there. uh, Storm surge, damage structure, lot of impacts are there. So generally for tropical cyclone, the forecast challenges are genesis. Genesis means the starting point of tropical cyclone. Track Tracking how the cyclone is going. Forecast track what direction it will goes and which location it will touch the cyclone, where will be the landfall. So evacuation is required. Indian disaster management or Indian meteorological department, they are doing this tracking. They are regularly monitoring if there is a cyclone over Bay of Bengal or Arabian Sea. So this is one of important for this forecast challenge. Then maximum intensity, what will be the intensity means what will be the wind, because intensity is damage potential is proportional to the nth power of intensity. Huge, if intensity is huge or wind is huge, then damage potential will be huge. So this is one representation of 1999 Odisha cyclone. Long back it's happened. So this I use for global circulation model LNDGCM. This is very old forecast, and resolution we can see that resolution of that forecast is 50 kilometer by 50 kilometer, and vertical level we using only 19. So this is old model, old run actually. I use in 2010 or 11. That just I would like to show the some structure. So it's showing very similar structure that time, and with high resolution. Sorry, with low resolution. 50 kilometer nowadays is very low resolution, because nowadays global model is running uh, uh, in India it's running 12 kilometer, then Japan is running 3 kilometer, 5 kilometer. So this is very low resolution, and this is the domain. Now coming to cyclone filing, this is 2013 cyclone filing. This cyclone filing occurred in October 12, 2013, and it was a strong storm hits India in 10 years, which has a high wind power. So this figure represent the radar data, Indian radar data. This is the observations, and this is the satellite data. This is the visible satellite data from Euromet. So we can see that the observations of that cyclone, and this is the forecast. This middle panel showing the forecast. This I use to run the model is I use WRF, weather research and forecast model. So these are the domain, three different domain I choose over, and resolution here 1 kilometer I use, and this is 24-hour forecast. So initial condition I put before 24-hour and forecast after 24 hours. We can see that it is very well matches with the observation. This is radar observation. So the how much accurate are there. So resolution also depends on the model, accuracy of the model. So this is 1 kilometer by 1 kilometer, and vertical level 51 vertical levels are there. So how it is nicely represent the forecast. Now this is 2020. Previous in one slide satellite data I have shown that one cyclone is there now, or hurricane Genevieve. This is the satellite observation. This is yesterday's, I think. Yeah, this is yesterday. Goes 17 visible channels, and this is the simulation model forecast. This is the global GFS model forecast, global forecasting system. Another model, global model in USA. We are using operationally this model, so we can see the representation of cyclone, how much accurate is there, and yeah, this is the composite reflectivity scheme. Now in severe weather, this is the small severe weather prediction. So severe weather is like tornado, wind, hail, storm, high intensity rain. So how in USA, the every day there is some events are there, and mainly in my location the lot of tornadoes are happen during the April, May, June, and the hailstorm, severe weather. So we for that we are running the small domain. This is the small domain over the region of interstate. So this is one example. I am not going through the details of this, but how we are predicting using numerical weather prediction. This is radar actual observation. This is the tornado is showing, and this is the model forecast. This is a 3-hour model forecast, and the resolution is very 3 kilometers. This is the small domain. So we need the more accurate forecast using the numerical weather prediction. So this is some result is I'm showing. So how much accurates are there, we can visualize the thing. This is one comparison between the observation radar reflectivity, and we can see the black spots are there. This is nothing but the model, and there is a tornado. This is my location, Oklahoma, Norman. So here this is my state where I am staying sitting right now. This is somewhere here my house is there. So this is the one of the most tornado prone area. So we need the more accurate forecast, severe weather forecast. So we are using the numerical WRF model with high resolution and small domain to predict the tornadoes or high weather, heavy rainfall intensity. So we can see that the model is very well matching with the observation, but there is a lot of challenges are there to predict more accurate forecast. So I am just going to finish my slide. Only 2 or 3 slides are there. So these are the some weather research and forecasting institute all over world. World Meteorological Organization, WMA, is the father of all. Means it's yeah, this World Meteorological Organization is used all over all the country. Then coming to European Center for Medium Range Weather Forecast. This is one of big organization over Europe. They are using the their forecast is very high, and they are doing the data assimilation and a lot of uh, activities, weather research with global model. And then Japan Meteorological Agency, Met Office UK, United Kingdom. Uh, then in USA, National Center for Atmospheric Research, National Ocean and Atmospheric Administration. This is NOAA, what I am doing, working now. And in India, Indian Space Research Organization, they are also doing a lot of research activities in weather forecasting. Ministry of Earth Sciences, where this Indian Meteorological Department is the branch of Ministry of Earth Sciences, and National Center for Medium Range Weather Forecast. They are doing the meteorology atmospheric related work in India, then Canada Meteorological Center. So there is a then lot of agency. Every country needs the meteorological center, so weather forecast. So almost every country has their own department, and these lists are the most important weather center all over world. So coming to the applied mathematics, so we can see that the mathematics has a huge scope or huge application in, especially in atmospheric science or weather forecasting. So today I just show only few examples, and a lot of examples are left. And so in future, what is the future of applied mathematics or applied mathematics? Nowadays, artificial intelligence is one of the hot topic all over world. Artificial intelligence in the exploiting of satellite observation and numerical weather prediction. Because artificial intelligence already has done a lot of works in other fields, including medicine and medicine, then computer science like Google, and then a lot of things artificial intelligence has done. So we are in weather, numerical weather prediction or satellite data, we are trying to implement this artificial intelligence. So this is the one of the future application of applied mathematics. Artificial intelligence, machine learning, deep learning, these are the nothing but the application of mathematics. Where if this Google has recently created this TensorFlow. TensorFlow, this is one package software for machine learning or deep learning. These nowadays many software company they are using this one. So we are also doing research on that, and these are basically based on mathematics. So, and the concept of machine learning or artificial intelligence is like that. What I have just showed we are doing numerical weather prediction with some rules. Rules are nothing but the model and data with classical programmings, and we are getting the answer, means the output. What machine learning is doing, it is creating the rules, means formulas. It is creating the formulas using the data and answer. So this is quite interesting, and there is a huge application of mathematics, including all the mathematics starting from linear algebra, advanced algebra, statistics, these things. So here one examples. Actually, this one I have done in for tropical cyclone forecast in India during 2011. So here it's showing the cross validation, training and collaboration. What machine learning is doing nowadays, the machine learning what it's doing. Suppose this is one equation. This is a non-linear equation. So it's alpha and beta are the parameters. We have the raw forecast, and we have to find the pattern of that forecast. So we have to find the alpha and beta from set A events. So this is called training set, where we have to find from data, we have to find the alpha beta, and we apply the same alpha beta in the set B event. This is called cross validation. What this machine learning or artificial intelligence is doing. So this is small example I just took. This is another topic, and it is quite interesting. The application of mathematics in future. So thank you very much. This is my last slide. Thank you very much for your attention.
Thanks a lot, sir.
Thank you.
It was really nice and a wonderful session. You have explained everything so well, and you have taken so much time to explain. I hope it's clear to every participant who is attending this talk. Many a times my students keep on asking me, what is the application of those inner product? Why you are studying inner products, linear algebra, differential equations? So I think the students, my students as well as other students who are attending, they have got answer to this particular question, that in fact these are important.
Yeah,
Okay,
that's
so,
true.
yeah.
Yes.
So we will proceed. We have a number of questions in the comment sections also. We will take up those. Before that, we have another resource person with us who will be presenting on the third day. He is Professor Kolpal from Jadavpur University. So I'd like to get some feedback from him.
Hello.
For the session.
Hello. It's a very nice lecture and very nice talk. So just now Devashish told that how this mathematics, highly nonlinear type of thing, weather prediction is very chaotic, very nonlinear, and how starting from simple mathematics, you have explained very clearly that linear algebra, probability, and all these things comes into play, and you can predict so fine. In fact, being in Kolkata right now, West Bengal, so we have gone through this worst phase of this, cyclone Amphan, which is called actually. Yeah. So, and the prediction was absolutely right. So I think this modeling or whatsoever it is, they have done fantastically well. Right at this point, it will land in West Bengal, and how much speed and all these things, they have calculated it very well. And if we have missed somewhere, then we could not utilize the forecast actually because of this lack of our preparation for these disasters, right? But the prediction from mathematical point of view, from computational point of view, was fantastic. But I am interested in one thing. Nowadays, this quantum computation is coming into play. So do you think it will get better with this more of this involvement of quantum computation, these predictions and all these things?
Quantum prediction in my weather prediction, we are not exactly using the quantum prediction, because these are, I think it's related to relativity or
now what I want to mean actually this computational aspect which coming into play, but with the development of quantum computation, whether the predictions is going to improve a little more or not.
There is a huge chance to improving this application, because a lot of research is going, and obviously there is a huge chance to improving the application.
Okay, fine. And one another just comment, just I don't know whether it's logical to answer question it or not. Being in Indian Ocean, these cyclones are developing, and in the so Atlantic Ocean or Pacific Ocean, the hurricanes are developing. I think are people using different mathematical things to predict those models, or all the oceans mathematical things?
Yeah, mathematical things. Actually, what I have shown the numerical model nowadays. Actually, there is different way to predict. Today, I just showed the numerical weather prediction. There is statistical weather prediction is there.
Okay.
So it depends on the agency, what they are using. Generally, nowadays, numerical weather prediction is most important, because statistical, there is a lot of uncertainties there. So it depends on the model also, and obviously the location, region. What region? Bay of Bengal, there is a different characteristic is there, like
Right,
sea
right, right.
surface temperature. Temperature
Yeah.
is different over Bay of Bengal. Weather is different. So there is a that input data is one of important topic. This input data. So this input data is giving the more information about the cyclone or hurricane. So yeah, that's true. And another thing is there that it depends on the location also. This tropical region over uh, India, Bay of Bengal is getting maximum number of cyclone, and
Yeah.
Arabian Sea is getting less number of cyclone. So yeah, that characteristic it fully depends on characteristics, and the model is there. So different model are using. Although model, the concept of model is very similar,
Okay.
and the data is like different. Yeah,
Thank you. Thank you very much. Thank you. Yeah.
thank
Thank you, Devashish,
Yeah, thank you, sir.
for
We
hosting such
will,
a wonderful conference. Yeah.
yeah, so I'm putting you backstage now. We'll take up other questions. So there are several questions. Let me just have a look. Initially, at the beginning of the session, there was some question. Meanwhile, the participants can fill up their feedback form, which I have provided. Yeah, so there is a question by Mridusmita Das. Is there any high accuracy model to determine about the earthquakes and about the geofluid, like prediction of some volcanoes? What type of methods are used in those models?
Yeah, thank you for asking the question. Actually, this is like seismology. We call it seismological science. So this is in India, Ministry of Earth Sciences. There is another division. So actually, I am not. I never go this department. I don't have any idea about seismology because I am fully on atmospheric science, and I heard that there is no model for earthquake prediction. Means but I don't want to comment anything on that thing because I am doing in weather related forecast or atmospheric science, and this is another branch.
Okay. Okay, sir. So we'll take up another one here. Hmm.
By the way, I would like to one thing that earthquake. There is a tsunami is there. So tsunami, there is tsunami warning center in the Ministry of Earth Sciences, which is located in Hyderabad, in INCOES, Indian Oceanography. So they are doing some work on tsunami, not earthquake exactly.
Okay.
Yeah. Okay. Thank.
Okay. Then we have another question from Roosevelt Irungbang. In Lorenz 1963, probably he is referring to one of your slides, three variables model. How can we take the parameters sigma, uh, uh, has written something in bracket, Prandtl number and R Rayleigh number and B, and how we develop this differential equation?
How we'll develop this? Yeah, this is a Lorenz model. In that Lorenz model, 1963, the 63 model, there he described all the detail of this model, how we can change the parameters, value of the parameters, and the how it behaves like that. So there in that description in his paper, details are available on that model.
Mm.
Okay.
Okay, then I think we can take another question. So this is from Ritu Dhiman. After doing PhD in nonlinear partial differential equation, how can I join? How can I join that field? Means how can I work in weather forecast? Okay, sure. So he or she is probably asking after doing PhD, how can he or she join in weather forecasting field?
After doing PhD in non-linear
Partial
partial
differential.
differential, it
Yes.
depends on, see, a lot of applications are there in non-linear partial differential equation. So like atmosphere weather forecasting is the, as I told, interdisciplinary subject. So this is not only the partial differential equation. There is a lot of equations are there. Obviously, the chaotic theory and other things are there. So yeah, there is a chance in India, like India IIT, few organizations are there. They are doing the, but after PhD, yeah, after PhD, it's we have to do the research on the weather forecast.
Okay. So there is another question from Bijeta Pal. Sir, can you give a little insight on how to take up artificial intelligence as a subject, learn about it, and how to approach?
Yeah, artificial. This is one of the hot topic, artificial intelligence. So, nowadays, Google, or if we search the Google TensorFlow or artificial intelligence tutorial, lot of online books are there. Even in India, many people are doing artificial intelligence. So I think choose few good books for artificial intelligence, and it will give some idea. Even I can give some clue. If someone is expert in Python programming, artificial intelligence is nothing but programming. So Python programming or any programming, so they can download some script or uh, this package like TensorFlow package. Okay, then other libraries are there for doing the artificial intelligence, and they can do their own test if they're really if they're interested to learn the subject. And I don't think in India means in other means IIT or NIT, I am not sure they are teaching or not, but if they are interested, really interested, they can learn their own.
Okay, sir. We have another question here from Anuja. Is there any specific course or degree if someone is interested in weather forecasts, and which institutes are offering such courses?
Yeah, there is a in India there is, in our northeast. I don't think any institute are there. There is some institute like IIT Delhi, IIT Mumbai, then Cochin University, Kerala. But then uh, mm, this Odisha, some institutes are there. They are doing atmospheric research, but maximum uh, in other places like me. I am applied mathematics background, and I have done PhD in not exactly in weather forecast, but some related to weather forecast. So, if someone has done PhD in mathematics, they can join. Nowadays, means they can do research or physics. They can do research.
And sir, what about your institute? Not your institute, means the institute from where you did PhD, CMMax. Whether it is,
Yeah,
yeah, whether it is
seems
providing any specialized course in this weather forecasting and all.
actually now seems was actually seems full meaning is Center for Mathematical Modeling and
Medical.
Computer Simulation. So
Yes,
this
yes.
is CSIR model, Council of Scientific and Industrial Research, and this organization.
Yeah.
So that time I was interested on mathematical modeling. So mathematical modeling is nothing but weather forecasting. So seems are doing they are taking some students for PhD. I think they are
Yeah.
doing SSIR. I think they are doing PhD in
Yeah.
atmospheric science.
Yeah.
And even
So,
yeah,
yeah. Okay. Though, so interested students can have a look at their website as well.
yeah.
We have another question. It's basically a general question. Okay, just let us take up. Maybe you can say something on this. How can we develop differential equations? Means probably he's a student. He's asking means, how we develop differential equation related to some practical models.
Yeah, that I showed many heat equations are
Yeah, you
there.
already given examples.
Yeah, there are a lot of equations are there. So
Okay,
yeah, that
another
I
question. Yeah.
I think you will better answer that.
So if you have a look at your slides, maybe you can send the slides to me. I can share them with
Yeah,
via
sure,
email.
sure.
Yeah. So then,
It's,
if they have a look at your slides, also they will get to know. We have another question here from Priyo Kuman. Thank you, sir, for your informative session. Is there any equation other than Navier-Stokes equation for solving numerical weather prediction?
yeah, there is a lot of. I showed the basic equation of motion, which is the Navier-Stokes equation. But thermodynamics equation is there. Then continuity equations are there. A lot of equations are there. So, particularly in model, different equations are there. I have shown one link. There is a document. Lot of documents also there in that equation. So, is
Okay.
another research. Developing one equation is a huge thing. So we can publish lot of papers. We can do lot of work to develop one equation. So
Okay.
yeah,
Okay. So we have another question from one user, Captain Biom. So, sir, I have heard that no matter how we are smart and intelligent, we cannot predict weather more than 7 days in advance. So, if it is
I
true, then what is the reason behind this?
I don't know. Is it she or he? I am not sure. But
I don't know.
7 days, 7 days is too large. Even rainfall, we can't predict two uh, 2 days more accurately,
Yeah,
because
lots of uncertainty.
yeah, as I told that this atmosphere is chaotic, huge chaotic system. So 2 days after 2 days forecast, even meteorologists also can't believe after 2 days what will be the
Yeah.
accurate forecast. So even if the resolution high, then 3 hours, 4 hours also give the most important things. So yeah. So there is some slides. There is some slides. Even ECM, European Center for Medium Range Forecast, they have created every year that daily wise how weather is accuracy is reducing. So yeah, that's
Okay. Okay. There is another question from Chandramouli Chakraborty. He is my student. Now he is in ISI Kolkata. Uh,
yes.
yeah. So he is asking for solving the partial differential equation. Do we need to use Range-Kutta method or any other method?
Yeah,
So there
thank you for asking. Actually, I didn't told that I solved the Lorenz 63 model using a Rangekutta 6 method. So there is a Rangekutta. We have to solve this Rangekutta method only. Even in weather forecast model also we are using
it's
this
one of
method.
the most widely used methods, I think.
Yeah, yeah. It's thank
Yes.
you for asking the question.
Okay, so okay, one more question. Maybe the person is interested in pure mathematics. So prediction analyst need to be an expert in topology of the local area too. Oh, okay. Maybe he's asking, yeah, in topology of
Yeah,
the local area too.
yeah. Topology, we are not directly using the topology, but the concept is there. We have to we means
Means,
some
probably
uh,
he means to say the surface nature of
yeah,
the surface of the local area. By
yeah,
topology, he means to say this.
yeah. I use somewhere, I don't remember, but that was in topology. I learned one book that topology. There was some use. Yes, use is there topology, because mathematics is, see, I am talking about applied mathematics, but there is pure mathematics also there. Real analysis, linear algebra, these are pure
Yeah,
mathematics.
in fact,
We are,
functional analysis gives us
yeah.
the theory behind these differential equations. And all.
Yeah, so there is no particular that we are distinguished between that.
Yeah, yeah.
But yeah, topology also.
Okay, so let us take up another one. This is from Anurag Sau. Is the initial conditions or are the initial conditions taken in the function of, as a function of time? That is, can we also take as a functional form for modeling?
Yeah,
Okay.
yes, we have to take some methods are there, like 4D bar assimilation I told.
Okay.
So so different initial conditions are there for different forecasts. So time, we sometimes we are taking the function of time.
Okay. Okay. So that probably is a more complicated problem when initial conditions are taken as functional form.
Yeah, means initial condition functional form means suppose zero. We are forecasting starting from 0 hour. Okay,
Hmm.
0 hour. Then based on initial condition at 00 UTC, then 3 UTC. Based on the initial condition 3 UTC. So this is a function of time. So every
Yeah,
initial condition we have to create
changes with time. Changes
time.
with time. Yeah. That is more practical actually.
Yeah,
Right.
yeah. Because
Because there,
operational
with time
elements
there
are
are lots of changes. Yeah. So okay, another question probably it's more relevant here. Application of maths is everywhere. Then can we predict COVID-19 with the applications of LPP?
what is LPP? I am not
So,
sure.
yeah, linear programming problem. Yeah,
Yeah,
operations.
recently I read one article from Kolkata University. Someone has predicted using the
Yeah,
linear equation.
I think mostly those are statistical analysis. Means exact prediction of a particular germ. I do not know. What's
Yeah,
your view?
I am also not sure exactly. Yeah,
Maybe we can means the analysis means after the testing and all the analysis can be done. Statistical analysis can be done. How effective a medicine is. Those things can be done, but prediction
yeah.
of it is quite.
Uh, yeah, someone has written one article, Kolkata University, I think. I read, but that was not published article.
Okay, okay,
So they have predicted some 3 months prediction what will be the structure for COVID-19.
okay, okay. Okay, another one here. What is it from? Arundhati Banerjee, being a student of applied mathematics without PhD, is there
Yeah,
any way to do weather forecasting related theories? Means
yeah,
is
yeah,
PhD necessary to join the weather forecasting area?
yeah. It's possible. A lot of people are doing, but
Okay, okay. Any
getting
projects and all?
getting projects, and
Okay,
this is not that. As I told, that meteorology or weather forecasting is not a means in India. It's not a subject. Means it is interdisciplinary. So
okay,
anyone can do that one. In USA also, many mathematicians, many physicians are there. My colleagues, they are doing the weather forecast.
okay, okay. So we have another one more question. So it's nice to see so many questions here.
Yeah.
Sir, how can I get more information on the butterfly effect? Subroto Banerjee.
That that one actually, if we read the Lorenz model, there one article is there. I can share with that model. Means link. They have nicely uh, nicely discussed with the butterfly effect and other things. Yeah.
Okay. Okay. So meanwhile, for all the participants, the feedback link has been posted in the comment section. There is one more question. I'm not finding it. It was posted quite some time back. I'll just copy it here. Maybe the last one will take. Just I'm copying it from the earlier comments in YouTube. Control C. It's probably okay. This was from Aditya Das. Sir, what
Okay.
do you mean? Most probably related to some one of your slides. What do you mean by this inner? Probably this is inner product epsilon 1, epsilon 2 in the matrix B, or
Yeah, that matrix error variance and covariance matrix are there.
uh,
So that covariance diagonal off diagonal matrix are called covariance matrix, and
hmm,
diagonal elements of a matrix is called a variance matrix. So we are using that one for this data assimilation, 4D bar data assimilation. So yeah, for error characteristic, we have to know the error characteristic of the observation and model.
okay.
So yeah.
Okay, so one more from the same person. He had posted it long time back actually. I'll just copy it here. Also related. Yeah. Yeah, this one. Aditya Das. How to choose initial conditions in real life situations? Means any
Yeah,
hint?
Real life situation means weather related situation or what? Means,
Most probably,
yeah,
or maybe a general question.
yeah, means
Maybe write one example. You already
I,
cited actually in your
yeah,
presentation.
initial, yeah, this data assimilation, what I told, the observation is required and model background is required. So to create the initial condition means starting point. We have to run for running the model. Yeah, to run any model, we need some input data, na? Input.
Yeah,
So to get a output. So this input thing, it
yeah.
depends on the situation.
It depends on the situation. It will come from the observation.
Yeah, observations and model
Okay.
information.
Okay. So almost we are done with the question answer session. Almost, I think I have taken all. If I have missed, please do not mind. There are lots of comments here. Okay. Okay. So with this, we come to the end of the talk. And for the information of everyone, sir is in America actually. It's I think, what is the time now, sir, in America?
Yeah,
It's
it is 12:30 at night.
12:30 at night, and sir probably did not have his dinner as well. So let us say goodbye to sir, and let us thank him for the wonderful presentations.
Okay,
So good
thank
night
you.
to sir.
Thank you. Good night. Thank you. Okay. Thank you very much for.
And goodbye to all the participants. We will meet for the next session by 11:45. The link will be active. You can have a look. Okay. Yeah. So by 11:45, the link of the next lecture will be active in the YouTube page itself, in my YouTube channel. So till then, goodbye.